Now the Diffie-Hellman exchange, which is going to be part of phase one negotiation, and as I said it before, is going to be that magic mathematical algorithm which is gonna make those two VPN gateways end up with that secure common key without exchanging it over the wire. Diffie-Hellman, again, it's not an encryption algorithm because, as we saw before in the cryptography section, it is a asymmetric private public key algorithm, which, as I stated at that point, not all algorithms are used for the same purpose. As I said at that point, most of the symmetric algorithms are going to be used to actually secure data in transit or at rest. Or in transit means to actually encrypt traffic to an IPsec tunnel, for example. While the asymmetric algorithms are going to be used for key management or signatures or authentication in general. So there we go. The Diffie-Hellman asymmetric algorithm in this case is going to be used as a key exchange protocol so that both VPN gateways end up with the same secure key back and forth. So it's, of course, it's not impossible to break, but computationally it's not feasible. For details, you can look in RFC 2412, the Oakley Key Determination Protocol. But to give you an idea of how Diffie-Hellman exchange works, of course, it's not exactly like this. It's just what I'm about to show now is just to have a, let's say, a simple understanding of what happens. But this is, of course, not exactly what happens behind the scenes. It's close to. So imagine like we have in here Alice and Bob. So we have Alice and Bob, which are my VPN gateways. And they need to, both of those VPN gateways, through the Diffie-Hellman exchange, they need to end up with the same common secure key. So what happens, Alice and Bob, both of them know those two common parameters, the P and G values. This is mathematical functions, a prime number and a generator. So both of them know those two values, they match, as I'm going to show you, because when they negotiate in phase one, they're going to negotiate which Diffie-Hellman group to use, which based on the Diffie-Hellman group being used, they know what are going to be those values, the P and the G values, the prime number and the generator. So both of them know the P and G. And then what happens, let me put in here a separation. So Alice is a VPN gateway, Bob is another VPN gateway. Then what happens, both Alice and Bob locally derive a private key. This A number, which is randomly chosen by Alice, it's a big complex number. This is the private key of Alice. And B in here is going to be the private key of Bob, the other VPN gateway. So they locally chose those numbers. They don't send those numbers over the wire. Each of them has a different private number. Now what ends up happening further on is that both Alice and Bob derive a public key. So that's going to be the public key of Alice and Bob. A, this is going to be the public key of Alice. B, the public key of Bob. To derive those public keys, they make use of those common parameters P and G and their private keys. So this is the public key of both Alice and Bob. Public key and public key. And then what they do, they exchange that public key. So Bob sends its public key to Alice. They're going here. And Alice sends its public key to Bob. And this is going to be visible in clear text. If somebody sits in here in the transit path, they're going to see those public keys back and forth. But that's not a problem. And then after they exchange the public keys, they don't exchange the private keys, just the public keys. Both of them to another mathematical formula, logarithmic formula. Both of them, what they do, using the other side public key and the local side private key and the P and G numbers. So like if you take Alice, so Alice uses the G and P values, which were commonly known to both Bob and Alice, G and P. Then it uses the private key. Alice, of course, uses its private key and uses Bob's public key as well in there, and they end up together with the same K value, where the K value is going to be that common shared secret key. But they don't exchange that value over the wire. So this is at a basic level, at a fundamental level, how the Alice and Bob, how the VPN gateways end up with the same common shared secure key without exchanging that value over the wire. It's called a private public key algorithm because, as we saw in there, they exchange the public keys back and forward, but they don't exchange the private keys as expected. But then through that mathematical algorithm, they end up with the same common shared secret key. Now, phase 1 can run in two modes, main mode or aggressive mode. Why do we have two modes? It's a long story. Now, main mode is usually seen in side-to-side VPNs. It's longer to negotiate. It's going to be 6 unidirectional messages, where first 4 messages are in clear text because they have to send back and forth the ISACAM policies, those public keys, and the last 2 messages are going to be encrypted with the secure key material derived by the Diffie-Hellman exchange. And then we have the aggressive mode, which usually is seen in remote access VPNs, which is faster to negotiate, and which means it is going to have 3 unidirectional messages, not 6. And only the last message is encrypted, which is technically speaking not mandatory per RFC. We had, based on how IP1 works, we had to have 2 modes, because aggressive mode is a requirement in remote access VPNs with pre-secure authentication, and it's a long discussion to explain why. It's not in the scope of the CCNA exam. So now what they negotiate actually in phase 1. We saw what was the scope, how the Diffie-Hellman works. What the peers negotiate is they negotiate in clear text, of course, the ISACAM policies, which consists of 5 attributes. The authentication method, which we spoke about, the encryption, which we spoke about the options, the hashing method, the Diffie-Hellman group, and the lifetime in seconds. And only the lifetime is negotiated to the lowest value, but otherwise all the other values have to exactly match between the VPN peers. Now what the lifetime is, the lifetime defines how long are the keys valid. So once they end up, the phase 1 is successfully built and they end up with those keys, both sides end up with the same keying material, then the lifetime defines how long are those keys valid, because you can imagine that we would want to change the keys periodically for security reasons. Now, based on that Diffie-Hellman group number in here, there you go. If this is Diffie-Hellman group number, let's say, which one? 1536, I think is group number 5. Yeah, it is group number 5. So if they will negotiate to use group number 5, then they know, so they negotiate what group number to use. And based on the group number, both sides know what is the generator, the G value, and what is the prime number, the P value, which, as you can see, it's a very big number in there. And of course, the higher the Diffie-Hellman group number, it means the more security is in there, because the higher the group number, it means those prime numbers and the random numbers they derive is going to be bigger, which means like 8192-bit number. So the bigger the group number, it means the bigger the prime number in there, which means it's more difficult to, let's say, computationally break. Now once phase 1 is up, the result is that I'm going to end up with a one bidirectional IKE security association. It's bidirectional because both sides are going to use the same key to further secure phase 1 negotiation and phase 2 negotiation, because that's the scope of phase 1, to derive those key material securely by both VPN peers. So now we can speak encrypted, we can continue the negotiation process of phase 1 and of phase 2 securely. So before the last messages of phase 1 and completely the full phase 2 is going to be secured, encrypted, protected as negotiated within the ISACM policies. So nobody's going to be able to actually see at that point what the VPN peers are speaking back and forward. Now what is an SA? So the SA defines the security used to protect the control plane negotiation traffic between the VPN peers. That's the IKE SA. And it's a combination of negotiated secure keys and cipher algorithms. So because they have negotiated the encryption method and the hashing method and the authentication method, the Diffie-Hellman group numbers, Diffie-Hellman group, then it means that once they end up with both VPN peers end up with a safe key material, then it means that those keys are going to be used to encrypt traffic with negotiated algorithm, to provide integrity with negotiated algorithm, and that's what an SA means. It's a combination of the cipher algorithms negotiated and the keys negotiated. It's a security association which tells both VPN peers when they send traffic back and forward to secure phase 2 negotiation, how are they going to secure that negotiation process. That's an SA. And of course phase 1 has to be up and running, has been successfully built for phase 2 negotiation to start. Now that phase 1 is up and we have that secure tunnel being built, that secure IKE or ISACM tunnel being built in between the VPN peers, we go to phase 2. And now the scope with phase 2 is to actually negotiate the reason of the IPsec tunnel. So if scope of phase 1 was to bring up a secure tunnel so we can securely negotiate phase 2, now in phase 2 actually speak about, okay, so why do we bring up the tunnel to begin with? What traffic do we want to actually secure to the IPsec tunnel, and how do we want to secure that traffic? So like in the end, if you look at in phase 2 what we negotiate, if you look back at our diagram, so we have those two sites again. And then once phase 1 is up, we can consider that we have, between those two VPN gateways, we have one secure communication channel is going to be the IKE tunnel. So, and that's going to be secured as negotiated. So now when we speak, this is going to be the IKE or ISACM tunnel. And now when we go to phase 2, we're going to negotiate, okay, what do we want to protect to that tunnel? Let's say we want to send traffic between this VLAN and this VLAN. So we negotiate phase 2 through this IKE tunnel, which means it's going to be a secure negotiation. And now we negotiate, okay, why do we bring up the IPsec tunnel to begin with? And upon successful negotiation of phase 2, two additional keys are derived from the phase 1 keying material by default. And those two keys are going to be used to secure the actual data plane traffic sent through the IPsec tunnel. So phase 2 negotiation is secured with the keys and algorithms as negotiated in phase 1. And then when phase 2 is successfully negotiated as well, then we additionally derive other keys, which we're going to use those keys to actually secure traffic being sent through the IPsec tunnel in the end. Now phase 2 can run only in one mode. It's going to be the quick mode, and quick mode is very quick. Basically it's going to be 3 unidirectional messages, and of course all of those messages are secured to the key material from phase 1, because that's the scope of phase 1, to be able to bring up a secure channel so we can securely negotiate phase 2. So now because the scope of phase 2 is to negotiate why do we bring up the tunnel, it means that in phase 2 the peers are going to negotiate what to protect. So what do we want to send in the IPsec tunnel? Traffic from subnet A to subnet B, for example. And that's known as the proxy ACL or the encryption domain. So what do we want to encrypt or to protect? They also negotiate the VPN gateways, how to protect, and that's going to be configuration-wise the transform set, which also the name tells you exactly what it is. Because when we want to protect data through the IPsec tunnel, it means we're going to transform the data, right? Because if we provide encryption, we're gonna scramble the data. If we provide hashing, we're gonna attach hashed values to the packet. So in the transform set, we negotiate how to protect, how to transform the data, which means to provide security to the data being sent to the IPsec tunnel. We're gonna negotiate, okay, how do we encapsulate packets being sent in the IPsec tunnel? And we have ESP or AH. That's the protocol. What is the protocol we use to encapsulate? If we use ESP or AH, what is the mode of encapsulation? Tunnel or transport. And then once the IPsec tunnel is being up, phase 2 is going to be up, what encryption algorithm do we use to securely send traffic through the IPsec tunnel? DES, triple DES, or AES. Because we want also to provide integrity to the IPsec packets, then we have to negotiate, okay, which algorithms are going to be using to provide integrity to the packets being sent to the IPsec tunnel, MD5, SHA-1 or SHA-2. And of course, we're going to also negotiate lifetime, which the lifetime in phase 2 can be in seconds or kilobytes, and it's likewise a negotiated value between the VPN gateways. And of course, the lifetime defines how long the keys from phase 2, which are going to be the keys used to secure the data plane traffic to the IPsec tunnel, how long are those keys valid? Now let's take it one by one. So the proxy ACL is also known as the crypto ACL or the encryption domain. And now based on the IPsec VPN tunnel configuration, because we have a lot of options, the proxy ACL can be either statically defined via an extended ACL, or it's going to be dynamically negotiated by the VPN peers. If proxy ACL is statically defined, which that's going to be also our use case with CryptoMap IPsec VPNs, now best practices require that it has to perfectly match between VPN peers. Like if one peer wants to secure traffic between 10.00/8 to 20.00/8, the other peer has to have the same configuration. That's what I'm trying to say with this in here. Now the encapsulation protocol, we have two options. We have ESP, encapsulated security payload, which is an IP protocol number 50. And if we negotiate ESP, then we're going to provide to the data being sent to the IPsec tunnel CIA, which means encryption, confidentiality, integrity, which means hashing, and data authentication, and of course anti-replay function. If we negotiate AH, which stands for authentication header, as the name states, I'm going to just authenticate, not encrypt. So AH is going to be IP protocol number 51, and it only offers IA, so no encryption. Of course, it has lower overhead because it doesn't offer encryption, but it's less secure because packets are being readable in the transit network because they're not encrypted. If you ask yourself, then why do we have also AH? For a lot of reasons, it's another discussion because AH does authentication differently than ESP does, and of course also because from back in the days they had to leave options because maybe somebody doesn't want to offer encryption, just authentication of packets. And also imagine that back in the days encryption was very expensive, so it was maybe good enough to just provide authentication of packets to make sure they are not modified in transit because encryption was very expensive at that point. Now, what is encapsulation mode? It can be tunnel mode, which adds more overhead because when I'm going to send the packets in the IPsec tunnel, if we negotiated tunnel mode, it means that we're gonna add a new IP header to that packet which is sent in the IPsec tunnel. So in tunnel mode, we hide the original packet IP source and destination. This is typically used for inter-site tunnels, which means for IPsec VPN tunnels between routers or between VPN gateways or between firewalls. Transport has less overhead because it doesn't add an additional IP header. It preserves the original IP header of the packet, of the initial packet, before securing it. And it's typically used for intra-site tunnels, which means when you bring up a VPN tunnel, an IPsec VPN tunnel, between two hosts, not between two VPN gateways. And now, AH, tunnel versus transport mode. So before AH, that's going to be the IP packet with the headers IP, TCP, so layer 3, layer 4, TCP, UDP, whatever, and the data. In transport mode, as you can see, we preserve the original IP header, and we only add the AH header to provide authentication and integrity. In tunnel mode, we of course add a new IP header, and then AH is going to be encapsulating the original IP header in there. Likewise, ESP is the same thing, only that ESP, because it also offers encryption, is going to have both a header and a trailer. But otherwise, both of them work the same way in transport and tunnel mode. In transport mode, they preserve the original IP header. In tunnel mode, they add a new IP header. Now, if we look at for example in here, and let me zoom in a bit. So this is the original packet, the IP header and the payload. If I use AH in transport mode, as you can see, the original IP header is being preserved, and AH is going to just encapsulate the payload, the data. If I use tunnel mode, then AH is going to encapsulate the initial packet as it was with both the IP header and the data. And we add a new IP header in there, which is going to be the IP addresses of the VPN gateways. And of course, ESP is going to be the same thing. So this is the original packet, the layer 3 header and the payload, layer 4 and the data. If we use ESP in transport mode, then as you can see, ESP is going to encapsulate, is going to containerize between a header and a trailer just the payload, the data, in the original IP header is being preserved. But if you use tunnel mode, then ESP is going to encapsulate the initial packet as it was between a header and a trailer, so also including the initial IP header, the original IP header. And of course, it's going to add likewise a new IP header to the ESP packet, which is going to be the IP addresses of the VPN gateways. Now, phase 2 result: upon successful establishment of phase 2, we end up with 2 unidirectional IPsec assays, because both sides are going to use different keys to secure traffic sent through the IPsec tunnel. Now, this doesn't mean that I'm going to have asymmetric encryption in there. So what's going to happen if we look up again into that example as before? So we have those 2 sites of ours, site A and site B, and we want to bring up an IPsec tunnel between ASH3, those are my VPN gateways, ASH3 and router 1. So initially what happens, the IK tunnel is being built. That's going to be phase 1. We have the IK tunnel being built. The IK tunnel. It's one tunnel because it means we have one bidirectional assay, which means both sides, the IK tunnel is going to be used to, in the IK tunnel, we send, in the IK tunnel, we negotiate phase 2 securely. And of course, both VPN gateways, because it's one bidirectional assay, are going to secure the traffic back and forth, going to encrypt the traffic back and forth using the same one key. Now, when phase 2 is successfully built, we end up with 2 unidirectional IPsec tunnels. One from ASH3 to router 1, and one from router 1 to ASHV. That's why we have two unidirectional assays as a result of phase 2. So there's going to be the two IPsec assays, or you can look at like a two IPsec tunnels, two unidirectional IPsec tunnels between the VPN gateways. So what's going to happen? Let's say we negotiated to encrypt traffic, to secure traffic to the IPsec tunnel between VLAN 94 and VLAN 47. As traffic flows from left to right and ASHV sends traffic in the IPsec tunnel, ASHV is going to encrypt traffic with, let's say, key A, and router 1 is going to decrypt traffic with key A. So still symmetric encryption. Now when traffic flows the other way around, when traffic flows from server A to router 4, which means traffic goes in the other IPsec tunnel. Now router 1 is going to use key B to encrypt that traffic, which means ASHV is going to use key B to decrypt the traffic. So still symmetric encryption, not asymmetric. So IPsec assays are going to, so we end up with those two assays, or those two unidirectional IPsec tunnels, which the IPsec assay defines the security used to protect the data plane traffic between the VPN peers, which means what are the keys, of course, and then also what is the encryption algorithm, what is the hashing algorithm, what is the encapsulation, ESPAH, what is the tunnel mode, tunnel transport. So all of those negotiated parameters of phase 2. That's the IPsec assay. And it's also, so it's a combination of negotiated secure keys, cipher algorithms, and SPI value, which SPI stands for Security Parameter Index, which is another topic which is not in the scope of the CCNA, let's say, exam. You just need to know that it's part of the IPsec assay, the SPI value. To give you a short glimpse of what that is actually, you can imagine that, just a basic overview, you can imagine that a VPN gateway has multiple IPsec VPN tunnels established. So the SPI value is used to uniquely identify on a VPN gateway an IPsec tunnel with a remote VPN gateway. So we know, okay, so when I want to send traffic to that VPN gateway, what is the SPI value, which tells me actually what is the assay for that VPN tunnel, which tells me how to encrypt the traffic using what algorithms, what keys, what hashing methods, what encapsulation mode, and what encapsulation protocol. That's why it's called a secure parameter index, to differentiate on a VPN gateway between multiple IPsec VPN tunnels. Now optionally, we have in phase 2, we can negotiate what they name as perfect for secrecy. So if that's negotiated, it has to be, of course, enabled on both VPN gateways. By default is disabled. So it's another, if you cannot enable it on one side only, because if you do that, phase 2 is going to fail the negotiation. So you have to enable it on both sides, or leave it disabled on both sides. What is being used for is that if the peers negotiate PFS, then in phase 2, once phase 2 is up, they're going to run an additional Diffie-Hellman exchange, so that the phase 2 keys are not derived from the phase 1 keys. Because by default, when phase 2 is up, the peers, both VPN peers, locally compute those 2 keys, which they're going to use to encrypt traffic back and forth to the IPsec tunnels, but those 2 keys are derived from the keys negotiated in phase 1. So that may not be, that's not very secure. And of course, this adds more security, but adds also more CPU overhead. And the Diffie-Hellman group that is going to be used by PFS does not need to match with the Diffie-Hellman group from phase 1. It can be a different group, stronger or less stronger, doesn't matter. Usually it's going to be stronger, of course. Now, because both the IC assay and the IPsec assays have a lifetime, those keys have a lifetime, it means that we have to do periodic rekeying, which of course now the lifetime is configurable and is negotiated. And the shorter lifetime means more security but more overhead, because they have to constantly, negotiate new keys. Longer lifetime means less security and also less overhead. So it's always a debate on depending on what you want to achieve. Now, before existing keys expire, so the IPsec tunnel is, of course, a technology which the peers don't wait for the keys to expire and then to renegotiate the keys. So before the keys expire, new keys are negotiated through additional Diffie-Hellman exchanges.